attending and listening. I've got a lot of information that I want to present. It's the accumulation of 9 years of research, science, and testing. So I'm going to move at a pretty good clip. And I'd appreciate it if we could maybe have all the questions at the end, otherwise I won't get through this. Dr. Mohammed Asharani is also going to chime in occasionally. He helped me with one of the larger studies we did at Boston University, so we'll work together, okay? All right, here we go. So we're going to talk about minimally invasive endodontics using photon-induced photoacoustic screening. And that's it. Right away, let's get one thing straight, okay? The disclosure. I was told to give a disclosure. So here it is right here.
Where's the magnification of something?
You can't see it? Oh, okay. I'm sorry. There you go. All right. I am the inventor of PIPS, and I'm the managing partner for a research company called Medical Dental Advanced Technologies Group. It's a private technology interest that we put together that performs related research for testing. It holds a number of patents right now for PIPS and receives royalties from Technology for Medicine. They're the only company that can actually use this PIPS innovation that we have right now. I have a practice. I was born and raised in Scottsdale, Arizona, and I practiced there for 35 years, solo, until 5 years ago when my son, Enrico Divito, joined me. I've got a lot of associations, but one of the ones that I'm the most proud of is this instructor position that I have at the Arizona School of Dentistry and Oral Health. It's a dental school that's located in Mesa, Arizona. And one of my contributions was to start a laser department. An actual department that wasn't an extra credit or a research department. It actually is one in which the students must actively participate in laser dentistry because I believe that's the future. They must actually pass proficiency so that when they graduate, they're actually able and capable to use lasers. Okay, the Arizona Center for Laser Dentistry. My son, Rob Divito, is with me. So let's get started. My objectives today are these. I want to discuss the advantages of laser-activated irrigation using photoacoustic screening versus conventional methods. I want to explore the differences between conventional thermal laser, what we all know about prior to photoacoustic thermal lasers, and the photoacoustic delivery. And I want to demonstrate the efficacy of debridement and disinfection using PIPS as laser-activated irrigation. Okay, anatomical challenges. Our challenge is the root canal system. Turn that up a little bit. All right. These micro CTs were courtesy of Dr. Obey Peters. And I think they kind of get us in a mindset of what's available and what's going on. Complex root anatomies such as these make it a huge, tall challenge for us as clinicians. And that's the world we live in. Complex apical anatomies. This CT scan was actually made available to me by Dr. Ronald Ordonal out of Brazil. He helped me with some PIPS testing, and he told me, why don't you show this in your lecture? What appeared to be fairly straightforward, 3 to 4 canals, is anything but that as we start to work our way down towards the apical constriction. Multiple portals of exit. We need help. These things are very, very complicated. You know? Then along the way, these micro CT scans I'm going to show you now were given to me by Dr. Tom McClammy, who was in Rio de Janeiro lecturing, and this gentleman called Bernardo Camargo came up with these. Did a really beautiful job showing some of the complexities that we see. Once again, I know you know this, but it's nice to kind of wrap your head around it. Try to see yourself trying to negotiate these canals with instruments, hand and rotary files. And I believe he was working on this as his PhD, is that right, Tom? PhD. There's where all the activity, right there. So, maxillary first molars, multiple portals of exit, complex. There we go. It's my hair when I get up in the morning like that. Look at this. These are buccal roots. Very, very complex systems. I'm going to show you today through a series of slides and videos why PIPS allows you to more effectively do this without changing the anatomy. It's actually a system that can be used that will more conservatively allow you to reach the apical 1/3, and you'll be able to do it without even placing the tip inside the canal. Very nice. Okay, we're all about improving outcomes. That's our whole preface, right? So, Peters in 2001 talks about all instrument techniques leaving at least 35% or more of the canal surface unchanged. Instruments don't get everything. I think we all can agree with that. Literature confirms it. Instruments create smear layer. We pretty much agree with that too. There we go. JOE 2000. Irrigants. Instrument shape, irrigants clean. It is my professional opinion that although instruments are necessary to shape the canal, I believe it's because they need to be done so that we can have a better opportunity to get our irrigation systems down to the critical apical 1/3 area. Effectiveness is proximity dependent. We all know this. If you can get the tip down near the area where you can have an efficient exchange of fluids, you might have a chance to actually kill and debride the area. But it's dependent on where the tip is. Yep. All right. So, International Endodontic Journal. Our friends Losiukas, Lambridis, and Castrinus, and I'll never pronounce that right, I know I butchered that. I just call them the BLK boys. They were very good at using computer-generated analysis, and what they found was that irrigant replacement was limited to the first 1 to 1.5 apical millimeters to the apical tip of the needle. So their conclusion was that irrigation needles should be placed within 1 millimeter of the working length to ensure fluid exchange. This is even applies to ultrasonic. Very sophisticated computer renderings showing that where most of the activity is where the side port is, some of it is apical. Nice, sophisticated. In a subsequent article that came out, they used this computational fluid dynamics to kind of evaluate the irrigant flow. And what they found was that the flow patterns of the open-ended needles was different from the closed-ended needles, resulting in more irrigant replacement in the front of the open needles, but also higher apical pressures. So even though the open needles created more flow, and that flow was critical as you approach the apical 1/3 because of extrusion. You'll probably recognize some of these. Here we have a flat tip, bevel. These are all open-ended. These are closed with side ports. And this is the endo. And when they did those computations, you could see where the open needles had quite a bit of forward movement, a lot of flow, laminar flow. But as you approach some of the closed ones, most of the activity was, once again, near the side port, which means that even these tips, to be effective, needed to have more of an opportunity to go around the curves, bend around the curves to reach the apical terminus. So, if you look at categories of irrigation, I kind of categorize them this way. You have manual irrigation techniques. techniques, which include syringe, brush, manual agitation. And then you have machine-assisted irrigation techniques, such as sonic, ultrasonic, and pressure alteration. What I'd like to introduce tonight is laser-activated irrigation, and you'll see it referred to as LAI in the literature. So let's talk a little bit about the histories of lasers in dentistry. And to do that, we have to talk about physics. Now, the purpose of this lecture is not for me to give you laser physics. That's a whole different animal in its own, and it would take at least 4 or 5 hours to really get you into it. But what I'd like to do is, I'd like to make it very basic. I'm just going to talk about why laser-activated irrigation using PIPS works, and then as you become more and more interested and hopefully get involved in laser-activated irrigation, you'll learn more about the science and the physics behind it. This is the electromagnetic spectrum. This is the area, of course, we see. Anything to the left is ultraviolet. Anything to the right is infrared. The ultraviolet includes things such as X-rays, gamma rays. If you go to the infrared, you'll see ruby, ND, neodymium, the HOYAG, diodes, erbium YAGs, and CO2. What we will focus on today is erbium, the erbium category. And the reason I'm focusing on that is because it has a very high absorption rate in water, which is how we create photoacoustic streaming. So, making it very simple, we're taking unexcited water molecules and we're highly exciting them because the photons penetrate to a depth of several microns. And that substantial mass of molecules actually accelerate out of the actual proximity of where their neighbors are, and they yield a real powerful droplet micropropulsion. So you get excitation, and then you get these macrospheres that are propelled. I'm going to show you those with some videos here in a minute. Before we do that, why is that important to us? Well, we have to talk about the penetration depth of chemical disinfection into the actual canal walls, all right? And as we go from the canals into the dental tubules, we see that there's a huge difference between the chemical irrigation that occurs at less than 130 microns using hand syringing, but the bacteria themselves actually penetrate clear deeper into the actual dentin. Using sodium hypochlorite in hand syringe is about 130. Laser, on the other hand, with diodes were shown. This is 8 years ago when I came to the scene, when I saw that really lasers weren't that accepted because lasers had some serious side effects. Some of the lasers that were used were able to thermally burn into the walls of the actual dentin and cause huge reductions of bacterial load, sometimes as much as logs of 4. That was the diode. Then another wavelength, which is also known to penetrate, an NDA, would go even further, almost 1,000. However, the bacteria have been shown to be all the way out to the periodontal ligament. So you have the lumen, you have the dental tubules, and it goes clear to the periodontal ligament. All right? So, let's talk a little bit about the previous laser technology. 8 years ago, when I entered into this field, this was the technology that was available. These tips were FDA approved by the manufacturer, and they were approved for endodontic applications. The problem was the protocols weren't really there. So this is the way we were instructed to use them. The tips were lowered down into the canal, and then sequentially they were removed. And as they were removed, the laser would fire, and thermally it would begin to burn the inside of the actual tooth and penetrate into the canal walls. All right, let's see if we can do this. I think my laser pointer's running out. Previous dental. All right, so here we have a diode laser, and it's being lowered into this canal. And then sequentially it's going to be removed, and here's what we saw. This is the previous history, okay? Oh my word, was that smoke kicking out of there? Yeah, it was thermal. It was a huge thermal effect. This is what gave lasers a bad rap to the industry, in my opinion. This is why when I talk to most dentists, they say, well, I've heard lasers don't work, and so I'm not going to go in that direction. Hopefully you'll reconsider that when I talk to you about photoacoustic approaches. Our scan showed that there was charring, crystallization, burning, and where the SEMs would actually even show that these surfaces were no longer pristine, natural. Ledging, ditching, and look at the wattage. Now, you don't know this, but this is a very high wattage, 1.5 watts. That's what was advocated at the time. The wattages I'm going to show you are well below a half a watt. And there's some huge implications for that. So the traditional near-infrared morphological effects at the working length, down by the apex, were burning. These teeth, you could actually see where the thermal damage was done. So whether it was ND or diode, these were the two that were advocated at the time, this led to that. Without being an SEM expert, you can kind of look at this and say, you know, these don't look right. They look melted, they look burned. This looks like the surface of the moon almost. It's just, you know, not right. So, traditional lasers cause this. This is what we were hoping for. Very nice, clean surfaces. However, this is what we have. Thermal. Very thermal effects, okay? That was with the diodes. By the way, the diode is the most popular entry-level laser right now being used, and when I talk to doctors and they say they use it, diodes are good as soft tissue, but they're not really good in my opinion. I don't believe they're as good in my opinion as what I'm going to show you because they have a thermal effect. Same thing here. We were hoping for surfaces like this, but instead, we got these. Okay? Now, remember I told you what I'm going to show you is the erbium family, the one that's highly absorbed in water. Well, even the erbium at that time, although it was better, there were more open tubules that you could see, there was still thermal effect. So I kind of went on this quest to see if there was some way that we could maybe use the advantages of erbium, but in a different way. So, old technology, and I'm going to show you some new technology, okay? The PIPS technique. Once again, PIPS is an acronym for Photon-Induced Photoacoustic Screening. Photons are particles of light, excuse me. Photons are particles of light that are highly absorbed in water if they're at the erbium wavelength. And they induce or cause an acoustic shock wave to occur, and that shock wave is responsible for the streaming. So that's how I came up with this acronym of Photon-Induced Photoacoustic Screening. Lasers were brought to the endodontic arena in the hopes that they would improve on the traditional results through the use of light energy, and that would be improving smear layer removal, debridement, and decontamination of the complete endodontic system. Episolo talked about the classic approach typically results in an ineffective irrigation. And then he went on to say that there were other mechanical devices that had been developed to improve penetration and the effectiveness of irrigation. He also talked about the effects of agitation on tissue dissolution was greater than that of temperature. And continuous agitation resulted in the fastest tissue dissolution. This was a turning point for me. Because I said to myself, if we could get the laser to increase the amount of agitation, we might have a chance. So, PIPS uses these photons of emitted pulse light and creates a pressure wave or a shock wave that allows for a three-dimensional movement of the irrigant throughout the entire canal system. It effectively distributes these irrigants throughout the root canal system. It uses a unique patented PIPS tip design, which I'll show you in a moment. And here's the key. It's got passive placement into the coronal aspect. The tip does not need to be introduced inside the canal. How good is that? As clinicians, if we can have some effect distant at the apex without having to lower an instrument or a tip into the canal, that would have some advantage. So with that comes the ability to avoid the need to enlarge the canal. Avoid the need to negotiate the tips around curves. And it also avoids the possibility of apical extrusion because you're so distant from the apex, unlike other irrigation techniques. All right? And the other part that's interesting is it avoids the need to irrigate the canals individually. PIPS will allow you to irrigate 3, 4, 5 canals all at one time. And I'm going to show you that. And then, of course, vapor rump. So this is, in general, this is the actual shape of the tip. This is a actual fiber that's made either out of quartz, sapphire, or zirconium. It has a polyamide sheath on it. These are actually the fibers that are used for telecommunications, by the way. And through our engineering, we determined that if we strip the tip and cut these tips at a certain angle, laser light, which is collinear, it's one direction, we could actually get it to diffuse out and have an effect. So these are the tips. This is what you see, a generation of evolution. We went from thinner tips that were 200 to 300 microns, longer, to more shorter tips, more robust. Some of these tips that we came out with that were 200 microns to allow us to go down in the canals were barely the thickness of 3 human hairs put together. So they were very thin and they were also very fragile. So one of the comments from the earlier generation was that these tips would break. This is what it looks like in the handpiece. So what is this pip nut? How does it work? So the tip is placed in the coronal aspect of the tooth, right here. It is not lowered into the canal. The access opening holds a fluid, and it's activated, held pretty stationarily for about 20 to 40 seconds. I will go through the protocol specifically in a minute. And here it is. This is the PIPS method. Did anybody not get that? That's it. It's that simple. In fact, PIPS allows us to negotiate these very complicated canals all at the same time without having to try to negotiate down into them. So, I created this 3D animation prior to videotaping a lot of this. I'm going to show you right now how it looks. All right, so the PIPS tip is lowered into the chamber. This is the smear layer that we're trying to clean off. The tip will remain here, and you'll see the camera move its way down the canal. There's a series of shock waves, and these shock waves travel three-dimensionally wherever there's fluid. And you get this reflux of debris, both vital and necrotic tissue, biofilm, and all the possible contaminants that are inside the root surface. We know that it's effective because when we looked at it, we saw this. We got really excited when we saw it. We said, my gosh, it's like we sucked the pulp right out. And then we got even more excited when we zeroed in and saw even the fibrils, the collagen fibers were intact. They weren't melted, they weren't crushed, they weren't blocked. As the camera continues down the canal, our lateral tubules were extremely clean, very clean. So, previous method, PIPS method. No charring, no ledging. We became more optimistic. It's as if we sucked the pulp right out of the tooth. All right. So let's talk about the fluid dynamics. How is PIPS really working? The photoacoustic effect works something like this. Most of the light, because it's laser light, travels down the stem, and because of the bevel, it is diffracted into a more diverse pattern. So remember now, I'm taking laser light that's typically lined up one way, and I'm trying to get it to bend. Because we strip this tip here, some of the energy is also lost here. That's advantageous for us, because by doing that, we create shock waves that occur. And these shock waves travel wherever there's fluid. And it looks something like this. Now remember, these tips are not being placed in the canal, so we don't have to worry about any thermal damage. What happens is you get this rapid expansion in the fluid. It generates a shock wave. That pressure wave travels anywhere from 7 to 12 meters. This is meters per second, not millimeters. And when you've got a real small volume of liquid, Mohammed, how much liquid do we have in the canals?
100 microliters?
Maybe 100 microliters. And if you have these shock waves traveling at 12 meters per second, it's pretty profound. And then as those bubbles collapse, you get negative pressure, and the rapid cycling between bubbling and negative pressure causes shear stresses on the wall that clean the actual canal walls. So, we're going to take a PIPS tip, and we're going to hold it inside this large volume of water, okay? And we're going to see what the effect is.
50 microseconds, 50 millijoules, 15 hertz, PIPS tip.
Dramatic. And remember, this is a huge volume of water. All right. If we capture that one pulse, and this is all happening within 100 microseconds, you see that the tip, paper and strip, you start to get a bubble to form. That bubble forms, and it's almost 1,800 microns in diameter, as opposed to 300 microns from the tip. So what is that? That's 6 times the actual dimension of the tip. And then as the bubble collapses, you get secondary cavitation that occurs. And it's that cycling that cleans. It's almost like a power wash for the tooth. That's what I like to say. So to make that even clearer, I had Dr. Giovanni Olivi, our Italian master laser dentist, who's been working with lasers for many years, go to the Netherlands, University of the Netherlands, and work with Luc van der Sloot, Bergen and Machado. These guys are really good on fluid dynamics and imaging. And I asked them to see if they could image some of this. This is a very sophisticated camera that takes movies at 40,000 frames a second. Here you have the camera, here's the tip, here's the light source. Here's the results. There's the expansion, the contraction. These tips are so well done. Look at them. They're very fine metered, and the actual bubble is almost perfectly cylindrical or circular. All right. Now, I want you to notice up here at the top. Look what's happening in the water at the top. You're getting some sort of what looks like a movement at the top. See this? Well, this is a huge, huge volume of water. And in fact, one of the researchers, when I submitted, said, why wouldn't you use a tooth model instead of a large volume of water? Well, I had to start somewhere to get the information, so this was our beta testing. But watch what happens when you now place the tip inside a canal, cylindrical canal. Dramatic. You get the expansion of the bubble, and then as the bubble collapses, watch what happens up here. The fluid is drawn down into the canal, and then you get secondary cavitation that occurs here. Watch right about there. See that? So this recycling causes the shear strips, once again, on the walls. Very cool. Okay, so we took endo practice blocks, tried to visualize this. I'm a real visual guy. If I can see it, I can actually, work on it. And we saw that by placing the tip up here, you can get streaming that occurs clear at the end. Now I'm going to advance the tip just to show you where the tip is. I'm not advocating it goes in the canal. This is just for demonstration purposes. As I withdraw the tip, there's still dramatic fluid movement at the apical area of this. This is an advantage. This will help us do our debridement and disinfection. All right. Vapor lock. Here I am. I'm placing the syringe inside these practice blocks. I'm placing dyed fluid. Now I'm going to go ahead and aspirate it out, put it back in. And although I do it several times, I make some advancement, but it never really reaches the apical area. And that's the area that we're really trying to keep clean. Okay. Let's see what happens now, vapor lock, if we PIPS it. Here we are again. I'm placing the dye in there. I'll aspirate it. See if I can get it to go to the end. I can't. Place the PIPS dip in, and within seconds, the vapor lock is removed. The fluid begins to stream at the apical 1/3. I'm sorry. I gotta go back again. Hit the wrong button. Gotta separate these more. In all our cases, we found that if there was vapor lock, we could effectively remove it just by the placement of the tip inside the canal. Which means we can exchange fluids, the fluids that we're trying to get down there to help with the debridement and disinfection. All right. Then I took calcium hydroxide, a real thick viscous solution, and I placed it inside the main canal and in this lateral canal. And here's my irrigation tip. First I used high volume of water, just trying to see if I could remove it with the water. And of course I couldn't. And then I placed the PIPS tip inside, and the objective was to see if we could clear that thick material without actually going to the area. Here we go. I was pretty confident that I could clean this, but what about this lateral canal? Usually within 20 to 30 seconds, I've not only cleaned this out, but now look, even the lateral canal has been cleaned. And no file is placed in the canal at all. Advantageous. Lucy? Okay? All right, here we go. All right. I think Ben actually made these blocks available to me. These are clear endo blocks that have been cut out on the side. You see this area right here? Because it's flat, I had to create a well, a reservoir, and I used liquid dam. By creating that reservoir, PIPS only works when it's surrounded by fluid. I got tremendous movement of fluid all the way, streaming all the way through the canal. Even the lateral canals were streaming. The issue is this, is wherever there's fluid, PIPS will have an effect. And I thought, well, that's perfect, because in our world, the ability to get these very complex systems dry and not have any fluid, I think is a very low percentage. So now we have a method by which we can actually add irrigants and then use PIPS as the driving force to move them in and out the canal. Cool. All right. I'm often asked, well, how long does it take to actually cycle the fluids through? So I took a red dye, same access area here, placed the red dye in here. Let's just take a look and see how long it takes. Here's the dye, 1001, 1002, 1003, done. In fact, our studies have shown that if you place your solution, your irrigant of choice here, and you use a 30-second interval, the replacement of the fluid, it turns over 15 to 18 times in a 30-second period. So we're constantly replenishing it and getting really good fluid down for fluid exchange. I had my engineer help me. I said, listen, create for me a tooth that I can look through and I can PIPS it. And this is the first tooth he came up with. And I said, what is that, a fish or what? I mean, that doesn't look like a tooth. So I redesigned it for him. And we made some lateral portals of exit, and we had some anastomosis with them here. The thing I want to point out is this tooth is 40 millimeters long. That's why I put the quarter here. And here's the PIPS tip. I'm trying to show you that the PIPS tip would never be able to reach the apex. And it's 40 millimeters long. Let's see what sort of an effect we have. Is that on the speaker? Can you all hear that? Okay. Look at the dynamics of this thing. The tip is still located in the coronal area, but we get this streaming, this violent streaming. Now, it took 90 seconds to clear this tooth. You'll see that the coloration of the fluid is actually removed over this amount of time. I had to shut it off because my good friend Tom McClaney was in the room and made some comments, so we didn't have to listen to that. Okay? You getting it? Does it make sense? Following you through. Okay. I'm going to zero in right now on this apical area right down here just so you can see. Now I'm 40 millimeters away, okay? I'm not inside the canal at all. Certainly not something we, unless we're working on the Neanderthal people, I'm going to come up with this. Laser activated irrigation. All right, let's move on. I was in Rome last year, and I met Dr. Gambarini. He's a professor at La Sapienza at the University of Rome. And I showed him this, and he said, Enrico, he said, use this model. I mask often, so if you're using the PIPS technique and you have 3 canals, you have to PIPS one for 30 seconds and then another one for 30 seconds and then another one. And the answer is no. PIPS will allow you to do all 3 or all 4 or all 5 at one time. Let me show you. You can see the PIPS tip and the hub here, so we couldn't put it any further. I'm confirming that I'm only in the coronal area here. I'm trying to film this all myself, so a lot of it's a little shaky, but I think it shows it well. Look at the movement here. Look at this, off and on. I let that wax in there so you can kind of see how it cycles it back and forth and back and forth. Okay? All right. 4 years ago, I was filming this up in Whitefish, Montana with a good colleague and friend of mine, Dr. Mark Bologna, who actually was my mentor. He introduced me to lasers before we got to this innovation. And these teeth have been cleared by our biochemist. So they're clear teeth. The coronal part of the tooth is down here, of course. The PIPS tip is only in the coronal area, and we happen to catch this on film. We turn the PIPS tip on and look at this. 1, 2, 3, 4, 5 portals of exit were negotiated, and now 1 file was placed inside the canal. PIPS was able to effectively stream the fluid to the apical area. So we got really excited. We said, here's some visual proof that we can actually move the material around. Then we went ahead after. Let's see here. And we filled it. We used a flowable sealer. This is the actual shape of the tooth, the nerve inside that canal. We did that at that time because we wanted to kind of see, push it to the limit and see what the possibilities were. We actually PIPS that sealer into place. All right. So, Dr. Olivi worked with Marco Martignoni, which Dr. Tom McClammy made me aware he had some special models, clear tooth models, that he thought would be perfect to show how the effect of PIPS works. So, here you go. They slice the teeth longitudinally. This is pulp tissue that's been stained with dye. And now we're going to try PIPSing it and seeing what the effect is. You see this little loop right here? I was pretty confident, again, that we could get the larger portion, but let's check this loop out. If PIPS can clean this out, I think we have a pretty good chance of approaching more and more of these, you know, from a more, shall we say, better debrided result. You can start to see the activation. We're going to time lapse this because otherwise, you know, it'll take a little longer, but within seconds, 1 canal. Now we're starting to get the other one. Look at this loop is still here. Can we get this clean? Let's see. Well, there you go. Now this is clean, but still we have tissue here. Is PIPS capable of negotiating that without having a file or a rotary instrument put inside it? Gone. This is the side port needle that they're placing in there. PIPS works great as long as it's hydrated. All you have to do is keep it in hydration. So some of the testing that's been going on around the world without PIPS training, they're using the PIPS tip, they're putting water into the chamber, and then they're sticking the tip in. The water gets consumed, and then there's no more PIPS effect. So the few cases that come back with results that, although they're better than conventional, they're not as good as what we're showing, is because the technique isn't there. Training, as with any new technique, you need training. Okay? All right. Let's see if I can move this forward. Now, this next video is a really large video, so it takes a few seconds to download. Okay. Dr. Olivi in Rome, Italy, with Augusto Malantacca, took this tooth and they cut it. Augusto's the one who prepared this tooth, and by the way, I found out he prepared the tooth prior to that was used. And we're going to PIPS this. Here's the pulp tissue from here to here. What effect would it have? Let's look. let's see, advance it for me, please. I think this might be, should I advance for it? Good. All right. Hang on. Like I said, it was a really big file. Well, let's go back. Okay, now I'll go forward. I'll go forward again. We gotta wait probably until it finishes up. Okay, we'll have to wait. I'm sorry, like I said, these are like 280 megs, and so it'll take some time. We'll see this one again. Any questions so far? I know I wasn't going to take questions, but this might be a good time. No? Okay. Yes?
When you're showing these pictures in the previous one, is that water or hypochlorite?
That's hypochlorite. Mm-hmm. Yep. Yeah. When we use PIPS, we find that because of this reflux event, it actually takes the pulp tissue and lifts it up out of the canal. That's what I'm going to show you. Let's see now. Advance it just once. I'm not sure. All right, give me a second again. How come it's still here, but I can hear it there? Yeah?
I can't see it too.
Okay. So just go ahead and advance it then. Anyway, what we would have shown is the pulp tissue coming right out. Here's another example of this. I'm going to hit this. Hold on. See if it works here. Yes. The PIPS tip is held inside the pulp chamber, and within seconds, the whole pulp comes right up out of the canal, both the pulp and the delta, fibers, everything. We see this over and over and over again. It's one of the characteristics of PIPS, its ability to debride anything that's inside the canal and just lifts it up out of it. That previous one, you would have seen the pulp tissue also come out all in one blow, actually, inside the canal. All right, there you go. So, you see this all the time, having to catch this. Usually it's so fast it comes out that it's suctioned up right away immediately. Sometimes we get lucky. All right. So, placing the PIPS tip inside the tooth, we always get a tremendous release of effervescence and bubbling because laser-activated irrigation decreases the amount of reaction time that it takes for hypochlorite and EDTA to actually have an effect. So what would normally take 30 to 40 minutes takes 90 seconds if you use PIPS. There you go. We always get these extremely clean surfaces. I like to call this monkey face. It looks like a monkey's face. Very, very clean surfaces. Some of Dr. McClamey's work, PIPS. You get this opalescent look. I don't know, I've been practicing for 35 years and I've treated several thousand teeth, I'm sure. And even prior to PIPS, I would do my best to clean the canals. But I must tell you, when you use PIPS, the remaining amount of debris that comes out of there is staggering. You just look at that and go, oh my gosh, I was gonna seal that all inside the canal. And more importantly, I get this opalescent look. It's like a power wash. It's been scrubbed. The tooth has actually been cleaned that good. Okay, so I'm going to show you, here's how it works. Here's the PIPS tip, here's the irrigating canal, 30-gauge canal, and here's the suction over here. Continuous flow of irrigation we found is better than just placing irrigation and then taking it out and replenishing it. There's always 3-fluoride hypochlorite available. Our cycles are about 30 seconds, 20 to 30 seconds. Say again? Oh, I'm sorry. A little bit more for it. This was the third cycle that I placed inside. There's 3 30-second cycles, and of course, wherever you see the effervescence and the streaming, the bubbles, it means there's still organic tissue in there. After the third cycle, that bubbling and the streaming becomes greatly reduced or doesn't occur at all. You can see all that oxygenation activity thanks to PIPS. PIPS drives that fluid down into little nooks and crannies, fins and webs and anastomoses, and you get a really nice reaction when you have a little more chloride. It's hard to film and do dentistry at the same time. You're running into the machine, you hear everything. Okay. All right. Now, for demonstration purposes, I'm not advocating this, but throughout the world, more and more people are using PIPS, over 1,000, I understand, actual clinicians. And I can't stress to you how much training is important. Although the application looks simple, and it is, the protocol is very specific. So I've had people who are using YouTube videos to buy the tips aftermarket or who knows what, and then using them, and they're not getting the same results because they're not following the protocol. But I'm going to flood this rubber dam with hypochlorite solution. I'm not suggesting this, I just want you to see. And I'm going to hold the tip outside of the tube, and I'm even going to put it inside the tube. Okay, good. Look at this reflux then. Look at all the smear layer coming out of it. The tip is clearly not inside the tube. Yep. This is why those teeth look so clean when they're done. They're literally okay? So, isolation is huge, as it should be with anything. I teach a lot of general medicine. And I must tell you that PIPS is the easiest part of the whole training. I mean, some of them don't even use rubber dams, and they show them how to put rubber dams on it. So I know that's not this group, but I'm just telling you, it's a big, big deal. And then we use liquid dam in many cases also to seal up, because wherever there's an opening in that crown, and it's typically the margins, PIPS will start to force fluid up the side because it takes the least path of resistance. So there are certain nuances with PIPS. You must isolate beneath your crowns. You've got to make sure that you have a nice reservoir of water, etc. So it has its little ideas. All right. So this is a study that we did at the University of Southern California with Dr. Adam Finchman. He is the director of the Engineering Fluid Dynamics, and what I asked him to do is to test, we wanted to test the effects of PIPS. Now I'm going to show you this. These are actual measurements that they take in which they show not only direction, but speed. So the arrows, based on the length and the size, kind of indicate what's going on. And what we did was we took the PIPS tip and we placed it inside a vial of water, similar large vial, just until the polyamide sheath was submerged. And then we measured at the 3, 8, 13, and 18 millimeters away. We want to see what the flow was. We took the ultrasonic tip and we only placed it in 2 areas because the further away we got from the ultrasonic, there was no movement. So there was no reason to measure it with the other areas. And what we found was this. The typical velocity under the PIPS area was dramatic, a lot of movement. Up by the probe, there was some movement for ultrasonic, but down here there was virtually nothing. Ultrasonic, PIPS. PIPS is not a laminar flow, it is a turbulent flow. There's different types of flow rates, and that turbulent flow is what allows us to do exchange of irrigants throughout the whole tube. On this scale here, if you look, here are your 2 ultrasonic readings way down here. And these are your readings of PIPS. This will be the closest, second. In any case, they were always greater than what you had with ultrasonic. Okay, debris removal. Rikuchi talked talks about the fate of tissues in lateral canals and apical ramifications. And he specifically said that chemomechanical preparation partially removed necrotic tissue from the entrance of the lateral canals and their apical ramifications. But it was pretty clear that vital tissue in these canals was not removed by the preparation, and that it was associated with periradicular disease. He pretty much histologically proved it. So Dr. Olivi prepared a tooth, sent it to him. He did some histological studies, and here's what he found. This is where the actual rotary instrument went. You can see that perfectly cut out. But in the area where it wasn't, tissue was removed. All right. To do this further, we went to the University of Tennessee, and Dr. Adam Lloyd took these teeth that were prepared, and he sent them to me. And then I PIPSed them. So, pre-PIPS, this is what he saw. And he used conventional, normal, standard irrigation and rotary preparation. Post-PIPS, this is what we found. He also went to the apical third, pre-PIPS, post-PIPS. So to challenge it even more, we started taking small slices. We moved 2 millimeter slices down. We went 6 millimeters. Certainly, the further we go down where all that complex anatomy, we probably have a less effect. Well, let's see. Pre-PIPS, post-PIPS. 4 millimeter slice, pre-PIPS, post-PIPS. And then in the last 2 millimeters, I mean, certainly there we probably would have some debris, right? Pre-PIPS, post. In every case, there was an improvement. So Adam sent me a tooth, and he said, I'm going to prepare this tooth, and then I want you to PIPS it. Remember, Adam's in Tennessee, I'm in Scottsdale. I used the PIPS protocol, I sent it back to him. He imaged it, and here's what he saw. He prepared these 2 canals measly, and then I PIPSed it. All the anastomosis area was cleaned out. We popped the lateral canal over here, and oddly enough, did anybody catch what happened here? This tooth was an even instrument. Let me go back. I want to show you this. Watch right here. Look. In fact, the reason that looks like that is because there was still tissue in the canal. So when he put the radiopaque material in there and then scanned it, it couldn't occupy the space at the same time. And it didn't matter. PIPS lifted it out, and there's the natural shape of that distal root. More studies. Pre-PIPS. You know by virtue of this that there must be some blockage, some tissue, smear layer that's been pressed in there as a result of instrumentation. We actually moved a lot of that smear layer down into those areas. We PIPS them. Watch what happens. Some really nice results here also. Clear. Clean. Very, very powerful. All right. I told Adam, I'm going to prepare a tooth, and I'm only going to do it to a size 20. And I'm going to send it to you, and I want you to go ahead. It just serendipitously, he was working with another sealer from Brasser called BC Sealer. And here's what we found. Does that not excite you? Well, it gets me. A couple of years sleep, and I knew that was going to happen. I knew it. But anyway, okay. All right, so, very, very interesting. You know, the red would be before, and then after that was that same too. Okay, so, bactericidal disinfection, right? Confocal imaging. This is with my good friend, Dr. David Adamilio. who was at the time at Loma Linda University, helped me with these confocal images. Do you all know what confocal imaging is? It's and I'm a neophyte, but I'm just going to tell you from what I know, just what I can understand. It's one thing to kill planktonic bacteria, free-floating, but when you have biofilm, a stack of bacteria, your effect can be surface, but the ability to look down through that whole section can be done with confocal. It can actually look through the layers to see how effective you are at getting all the way through. It uses light to show us live and kill. What's his name again, David?
Kelly Tran.
Kenny Trent. This is his assistant, yeah.
No,
This is David Amelio, huh?
he was a resident.
Oh, he's a resident? Yeah, good guy. He was there that day. And then we also took the samples and we went to USC where they did the confocal imaging. And this is Christophe Chauby, I call him Shamadan, all right? Christophe Chauby, apparently one of the world's experts in confocal imagery, because when you do confocal, typically it has to be on a flat surface, because if it's on a curved surface, it's very difficult to focus. And this happened to be Chun King, who at the time was working on the plasma flame. I don't know if any of you heard about that, where they were using like a plasma flame to try to kill biofilm, so she was there and got a chance to look. Okay, so here's Christophe preparing the samples. This is the confocal machine. The samples are placed inside here, looked at through the microscope, and then the information is sent from here over to the computer. So here's laser treatment of intercoccal efecalis biofilms. Now here's how you read these, okay? If you look in the microscope to try to look at these bacteria, here's what you see. Forget about this. This is what you see. It's gray, and you can't tell if they're alive or dead. But by treating them with a special solution and then shining the green light, if they're alive, they glow, they fluoresce, they're green. And if they're dead, they turn red. So if you take this and this and this and put them all together, this is your composite shot. So that is overlaid on that, which is overlaid on that. That's what it would look like, okay? So what we're looking at here is the little dots are live bacteria. If they were dead, those little dots would be red dots here, but they're not. So what is this red line you see here? That's autofluorescent. That's the light reflecting off the surface of the tube. So untreated controls, live. Here you are. You don't see these green dots here. That's just a reflection of the red light off the lumen of the actual specimen. And look what we have here. We've got bacteria that are infiltrated into the dental tubules. You can see them growing right in there, and these samples were taken towards the apical third. David did this really cool video. I like to include it. You can see where the actual efecalis is growing down into the tubules. Of course, those tubules go the full length of the tooth, so that's the frame that you can get. There you are. This is 200 microns. This represents 200 microns, and of course here your bacteria going clear out to the periodontal ligament that I'm showing. These are some nice photos that David did at SEM showing these bacteria that harbor inside these actual canals. So they took the positive group and they looked at the coronal third. Here we are. Here we are. Here's your efecalis right here. There it is right here. Same thing on the other side. They're just living, talking to each other, communicating with each other. Middle third. There they are. Going right down inside the tubules. And then the apical group. No treatment. Now this is with no treatment again. These are efecalis. You know, these cracks that are here, that's part of the process where they draw the vacuum out. That's not part of the actual tooth. All right, so now we're going to use laser with sodium hypochlorite in PIPS. Green is live, red is dead. Nothing. No sign of dead bacteria anywhere, just autofluorescence. In fact, I know there was a little hesitation because I know Christophe at first when he looked, if you remember David, he kept looking and he kept looking at the machine and he couldn't understand. He said, well, you know, I expected to see dead cells, I just didn't expect to see no cells at all. PIPS not only lysed and cleaned those cells, it actually pulled them right off so there was no bio load, what is that material? Your study showed that it removed the biomaterial or bio load, or what was it?
Yeah, the bacterial load.
Yeah, bacterial load, yeah. It was a special term. Okay, this are these right here. So using erbium and PIPS, we got a penetration depth that was greater than 1,000 microns. Much better. And the SCMs, this is what they look like. Look how clean these are.
Is that all still, it's just water?
Say again?
Is that 1,000 microns, is that all still just water? Not like,
No, that was hypoflow. Yeah, it was hypoflow. That's a good question. I'm going to get back to that. Very, very clean surfaces, okay? The question was that with hypochlorite or water? These tests were done with hypochlorite. Okay, so people ask me, all right, that's great. What's the scientific validation of all this? Well, we have ongoing studies that are still going now. But we worked with the University of Pacific. That's where I went to dental school, and I had a chance to work with Ove Peters. Actually worked with my undergrad at Arizona State University in the Center for Bio-Optical Nanotechnology. We did some confocal preliminary testing. Loma Linda University, University of Genoa in Italy, through Dr. Olivi and Stefano Benedicenti and that group. I worked with LSU and Van Hemmel, I believe is his name, was there. USC. And then we worked at Boston University, Mohammed and I. In fact, our article just got published in Photomedicine, and I'm going to show you. And of course, I was working with Tennessee, so I had to do that, and everybody got up and clapped because, you know, Tennessee and LSU and all that stuff. So, there you go. So, one of our studies, our first study, was published in the Journal of Endodontics. This was my coming out. PIPS was coming out. We were gathering information. And in that article, we talked about the disinfection of root canals using PIPS. And the conclusion was that there were more negative generated bacterial samples and left less apical bacterial biofilm than ultrasonic air activation. So at that time, Ove said it warranted more investigation. And we published in Lasers in Medical Science. And for those of you that don't know this magazine, as you become introduced to the world of laser science and endodontics, this is another major impact journal similar to JOE. It has a large gathering, and it's a scientific article that carries a lot of weight, journaling. What we did there is we looked at the effectiveness of the erbium YAG laser with this new radial and strip design. And the conclusion was that the well, I won't tell you what the conclusion was that the laser showed significant better smear layer removal than traditional syringe irrigation. Some more positive information. So then we went a little further. The Journal of Laser Dentistry, it's another well-known impact journal. Here we have Dr. Colonna and Dr. Olivi and I who did this together. And what we found was, the conclusion with this was that the studies demonstrated the effective of an erbium YAG laser equipped with a tapered and stripped tip set at very low energies and short pulse duration to clean the system. And that system, the technique, appeared to have no thermal effects on the walls, and the placement of the tip, which was remote and stripped from the target site or at the orifice of the root canal, the dentin surfaces and the collagen fibers were essentially undisturbed and clean. We published in Roots. We talked about the effects of different lasers. This is the old style, placing the tip clear down there, causing the burning and charring. We talked about the difference with that versus PIPS. This was published in endodontic practice, where David Armilio, myself, Tom McClammy, and a few others, we talked about the effects of streaming and for E. facalis. It was a pilot study, but the summary was pretty incredible. 20 seconds of the radiation with the erbium YAG laser and 6% hypochlorite completely inhibited the growth of E. facalis when compared to the combination of erbium with just water. So even if you use the laser with just water, you get movement and debridement. and you also get some kill, but you don't get 100%. And yet the dental shavings eliminated 100 of the fecalus compared with the combination of erbium laser, which is saline. So these were also beneficial. Bacteria in the tubules, this is what we're going for. Okay? How am I doing on time? Am I all right? Anybody know?
7 minutes.
7 minutes. Okay. The AAE issued a position statement back in November, I think 2012. What they talked about was another line of experience suggesting that the propagation of acoustic waves emanating from this laser may aid in distributing disinfecting solution more effectively across the canal, and they call it photon-induced photoacoustic streaming. So even your organization recognized that something was going on there. All right, here we go. All right, accepted publications. This is our publication that we did that was accepted in photomedicine. It's from Boston University, from Mohammed, and I think it was Dan Nathanson and George Wang. And the study showed that the activation of sodium hypochlorite with PIPS for 90 seconds, along with 90 seconds of rest time in between, 30 seconds on, 30 seconds off, 30 seconds on, was effective at achieving near zero growth rate of fecalus. Okay? This is your own journal. This month it just came out. Here you are. Talked about the elimination of tissue debris inside the canals. And the conclusion was that the PIPS laser-activated irrigation was able to significantly improve the debriding by 2.5 times. I want to read this to you for a second here, okay? Because this is something that Dr. Lloyd put together. He's the expert with micro-CTs, and here's what he said. He said, in the micro-CT that's on the left-hand side of the screen, you can see that the root canal system following instrumentation with 3006 using profile vortexes. The assumptions on these micro-CTs is that wherever there's a bright voxel, radiopaque debris, they will appear as black in the image as the fluid is interchanged and is unable to occur in this area, so they couldn't get interchange. Irrigation with sodium hypochlorite was performed throughout the instrumentation to prevent blockage and followed standard best practices. Red represents the system before the subsequent irrigation protocol, whether it was PIPS or a standard needle irrigation. The middle image shows the canal change following the PIPS irrigation protocol. Note that there were previously isolated areas of hard tissue debris. No, go back. Look there. Can you go back one way? Okay, so the middle image showed that the canal change following the PIPS irrigation. Note that there were previously isolated areas of hard tissue debris surrounded by vital tissue, and those areas are now filled with green, indicating that whatever occupied that area previously has since been removed, allowing the fluid interchange in that complex system. This means that PIPS irrigation method has removed hard tissue, allowing the irrigant to get where it needs to for the canal disinfection. And then the image on the right is a composite of the two left images showing the difference between pre and post PIPS technique and the amount of volume that was changed. This slide shows that the sample was prepared in the same manner as the above, the previous one, but this tooth only underwent standard needle irrigation subsequent to the canal instrumentation. With no agitation or laser-activated irrigation, the isthmus remains red with no change in the canal volume. The dark voxels remain dark and no change in the volume indicates irrigating with the typical side-bended needle to be less effective at removing debris. So turbulent flow in the complex non-separated anatomy is what is required to get canal disinfection. He also said that calcium hydroxide as an intracanal medicament is unable to enter this area if it's blocked with dystrophic calcifications, or worse still, packed with infected debris, creating a canal preparation that harbors cultivatable pathogenic microbiomes. Only adequate right there. Okay. So, in review once again, we're almost there. Published articles. We have many. Let's see. Quite a few international. These have been accepted already. This one was our most recent accepted. It's going to be in JANA. So we have plenty of science for those of you who are interested in looking into this and raising the level of your endodontic treatments. So my conclusions are that the advantages of PIPS are to reduce instrumentation, irrigate multiple canals, non-thermal event, effective 3D irrigation, enhanced activation of irrigates, ease of use, that's a big one, superior seal layer and debris removal, enhanced sodium hypochlorite effect, and effective against biofilm elimination. Now, what presentation in endo wouldn't be complete unless we showed some cases, because the thrill is in the film, right? These are some of my cases that we did. Conservative, very conservative. Retreats, PIPS is excellent with retreats. It opens up these areas, and once you'll see there's multiple portals of exit. Look at all these portals of exit that occur. Different angle there. You get the starburst effect, and I'll explain that one. It's kind of an interesting deal. Here, Dr. Mark Malonis with his work. Very conservative areas. You can see where there's some anastomosis crossover here. How about this one? Multiple portals of exit, 1, 2, 3, 4. You get some really, I'm telling you, when you use PIPS, you start to see all sorts of damage. It just opens up, it allows those fluids to fill. There we go. Here we go. This is Dr. Tom McClammy, the man, the clam dog. Look at some of this work. Very, very nice. Dude, you must have been on some serious drugs to do this stuff. Huh? Look at this. Look at these. Look at these shapes. Remember that little loop I showed you on the clear tooth? Here it is right here. Nice. Very nice. Molaris, intraradicular, what do you call this?
Entomolaris.
Intramolaris, yeah. Very nice. Dr. Olivi trains for PIPS in Rome, and a gentleman, a dentist, came from Torino, and he taught him this. Check this out. This is what he thought was a kind of an interesting, an extremely long tooth. It's about 28 millimeters long. Using PIPS, a very conservative approach, this is the kind of fill it is. $25.04. So, I brought this up because I took this quote from Dentistry Today that Steve Buchanan said when I asked Carl Ryder, retired but renowned prosthodontist from Newport Beach, what he wanted most from his endodontist. He said he would prefer that the endodontist could just suck the dying pulp out of the tooth without removing any dentin. He made that statement back in 1990. PIPS sucks the pulp right out of the tooth. So, I'm a firm believer in this. I hope you all are too. All right, and then before we leave, I just wanted to leave you with this, okay? I created a website for those of you that are interested and want to find out more. There's videos, there's science, there's a way to get a hold of me if you need to. The tech for med people will be the ones that I'll refer you to for the training and the laser. but it's called pipsdogs.com. If you go to that, you can find out more. I appreciate you all staying. Those of you that were awake, I appreciate you staying awake. Okay. Yes, sir.
How much hypochlorite is going inside the tube?
Well, let's talk about that, apical extrusion. Well, because the PIPS tip is placed distant, and it's a reflux event, the pressure never gets higher at the apical terminus than 5.7 or 5.8, which has been determined to be the intramedullary or intraosseous pressure. So if the PIPS tip is placed down inside the canal, just like a hand syringe is placed inside the canal, and you bear down hard on it, you could conceivably exceed the intraosseous pressure and force it out. But because it never gets that high and it's distant, we have very, very few incidents of apical extrusion. Now, I can only talk for myself. I've done several thousand teeth, and I've only had one incident. And that one incident was because the tooth was busted off at the gum line, and I was a little bit lazy, and instead of building a nice reservoir, I stuck the PIPS tip inside the canal. And if you approach the apical area, just like a hand syringe, you can actually increase. However, when I saw that happen, I turned the water feature on this laser unit, and it flushed water through there, and it cleaned all that area out. I had no post-operative effects.
What about those large palatal canals where there's no barrier right in the sides?
No, in fact, up to now, I can only tell you from personal experience, and I keep in touch with a lot of people. We haven't had any records or any reports of it. I can just tell you this, that if you follow the PIPS protocol, you can even use PIPS on deciduous teeth, which I don't know if you deal with. Teeth that still have open apexes, because there's that positive pressure, that's tissue pressure, it never exceeds it and it doesn't come out.
I have an explanation as well. Dr. Peters from Indonesia in 2013 published a paper where he used a radiopaque material mixed with 2.5 sodium hydrochloride. And once he started to irrigate the solution, he didn't notice any of the radiopaque material going beyond the apical area. Always when we're using the PIPS, it goes to the least resistance area, which is the middle of the canal lumen. So all of the cavitation goes back to the least amount of resistance, and you can see the bubbles comes out of the canal.
Yeah. Good question. Any other questions? I use this for calcified canals. I use it for retreats. I find it very, very, very useful. Okay, well, I appreciate everybody coming, and thank you very much. All right? Okay, great.
The CE number is W. What do you get again? Pencil. 150, 140, 5123. C. I'll repeat that. It's W150, 140, 5123C.